Good morning. As you heard, I'm from actually directly upstairs in the top floor of the building that you can't get to. And what I do throughout the course of the day is work on 3 different Mars missions. The Mars Reconnaissance Orbiter, which has been in orbit around Mars now since, well, getting closer and closer to 7 years, I believe. And I work on the HiRISE camera, which takes very high-resolution images of the surface of Mars. I also work on the Mars exploration rovers. They landed on Mars back in early 2004. 10th anniversary coming up next year. We'll have an exhibit here to celebrate that. Spirit hasn't been working for a while. We've canceled or ended that mission, but Opportunity is still perking along. And then the third that I work on is the Curiosity rover that you see up on the screens here. And my role on that is something that's called a strategic position. I'm a long-term planner, and what that means is, along with about 5 other folks, I work to establish what it is that we're going to be doing with the rover. Where are we going to drive to next? When are we going to drive there? Those sorts of things. And I do that on a daily basis. Yesterday and the day before, I served in that role and basically planned our drive away from where we've been working for the past number of months, starting our trek towards a place called Mount Sharp. So I'll talk to you a little bit about that, and I'll also describe some of the results of what we've been up to. So over here on the screen, you see on both of the screens, I guess, the Curiosity rover. To give you some sense of scale, it's about the size of a small car. This is a self-portrait that was taken when the arm here was extended out and the microscopic imager called Molly was turned back and looked at the rover and took about, I think, almost 50 images that were then stitched together into this mosaic. And what you don't see on the end of the arm here is a very large disc that serves as a turret that you can turn the various instruments on. And the reason for that is, in the self-portrait, it basically had to take that out of the scene so that we could see the rover. So what we see here is the arm, the missing turret, a mast that sticks up with several instruments up here. We have navigational cameras. We've got something called the mast cam, which is 2 different cameras. One is sort of a wide field view. One is a very narrow field view that gives us a lesser view of our surroundings, but a much higher detailed view of the surface. And then we've also got something up here called ChemCam, which is a laser that, much like this laser pointer, goes out onto the surface of the planet, creates a plasma as it vaporizes some of the rock material, and then there's a telescope inside that looks at that plasma and says something about the composition of the material. So it gives us a sense as we drive around with our cameras and our ChemCam what it is that we're driving by, what might be kind of interesting. Then down inside here, inside the rover, something that's new for Curiosity relative to previous rover missions, we've got 2 sort of chemistry lab experiments. One is called ChemIn, and that's a mineralogy experiment where we actually dump a sample into the rover, it goes to ChemIn, and it's blasted with X-rays that tell us something about the crystal structure and the composition within it. Is it clay? What kind of clay is it? Is it something mineral from basalt? If so, is it olivine? Is it pyroxene? Those sorts of things. And then also there's something called SAM, which is a gas chromatograph mass spectrometer, which is a fancy way of saying that you heat things up and burn them. And as you burn them at different temperatures, different kinds of material come off. And you can sense that in the gases that tell you how much water there is, how much carbon dioxide, how much carbon. Is that carbon perhaps organic? So we've got a very sophisticated payload of internal sort of chemistry labs, remote sensing up on our mast, and then we've got this set of instruments out on the turret that we can put down on rocks and tell us something about whether they're interesting, whether we can scrape off the dust, and is this something we want to drill into and collect a sample and put inside the rover to evaluate what's going on Mars. Now, the overall goal of the Curiosity rover is to establish whether or not Mars was habitable. We sent it to a place where we think that the past conditions might have been Earth-like, but we don't know that until we get there. And so the whole goal of the mission is to evaluate, to study different rocks on the surface and say something about whether those rocks were deposited in a place that was once habitable on Mars. Okay, so enough about the rover. Where is it? Well, this is a blow-up of a part of Mars. Remember, Mars has only got about 40% the mass of the Earth. So it's a lot smaller. However, because there's no oceans, The land area on Mars, the surface area, is actually about the land surface area above sea level on the Earth. So there's an awful lot of terrain to explore. And what's interesting about Mars is there's about a third of the planet to the north. The colors here show elevation, blue and purple being low, yellows, reds being high, where we've got a dichotomy between low terrain to the north and higher terrain to the south. And right along that dichotomy is a crater that's about 100 miles across called Gale Crater. And inside that crater, there's this huge mountain of material that we've dubbed Mount Sharp that sticks up. And that material is very layered. Let's zoom in on Gale Crater now. And we can see that within the crater, so we're seeing the north rim of the crater here. Here's the crater. So this ellipse here is that ellipse there. This pile of material that shows a sequence of layers that were deposited a long time ago. How long ago? Probably 3.5 billion years ago. So a period of time where on the Earth, we really don't have a very good record of the geology that was going on then. The layers in these rocks are kind of like chapters in a book. They record the environmental conditions when those rocks were deposited. So the reason Gale Crater was chosen is because it straddles this place on Mars called the dichotomy, and within it, it records, presumably, the events that shaped the surface of the planet during those early years. In addition to this stack of material called Mount Sharp, there's a river channel that's now dry that enters in from the north rim of the crater, and there's a fan of debris of sediment that's been sort of washed across the surface. If you've ever been out towards Death Valley, you've seen at the base of the mountains these fans of sediment that have been washed out of the valley, out of the mountain valleys. Those are called alluvial fans. And there's one of these right here in Gale Crater. So our twofold sort of exploration goals were to land near the Mount Sharp area, but also be able to detect and evaluate the sediments from this alluvial fan. So now I'll tell you a little bit about what we've been up to. Almost 11 months now, 11 months this coming Friday since when we landed last year. When we got to the planet, one of the other spacecraft that I mentioned I'm working on, Mars Reconnaissance Orbiter and the HiRISE camera, turned and took a picture of Curiosity as it was entering the atmosphere. And this is the rover hanging on its parachute. You can see a zoom in here. If you actually look at this in full resolution, you can see the cords and the parachute. Think about this. We're taking a picture of one spacecraft entering the atmosphere of another planet 110 million miles away. And it's got to be timed and pointed just right. This, to me, is an incredible statement about the capabilities that we have in space to do things that are just beyond comprehension to me, and certainly weren't things we could do 20 or 30 years ago. Now, once we got down on the surface, we used a process called Skycrane that lowered the rover down and then flew off. And this was a very complicated first-time approach to landing a spacecraft on another planet. And as a result of that, what it did is it plopped the rover down here with rockets firing off on either side that blasted the surface, and then the rover just drove away. And so literally, it's kind of like that old movie, Back to the Future, if you will, where you see these tire tracks streaking out in the distance and they just stop. In this case, the tire tracks just start and the rover drives away. So the Skycrane process got us down to the surface and left us on the surface basically ready to rove. Once we got down there, this is now a high-rise view looking down at the surface. Those blast marks that I showed you before are right here. The rover was sitting right there and it drove off. That's the rover, Curiosity, and those are its tracks. We headed off to the east because we saw some interesting things near where we landed in our orbital views that we thought we'd like to investigate. And that's kind of interesting because actually the area where we really want to go, this Mount Sharp area, is down here to the south and west. So we landed and actually took off in a different direction than we intended to before we got down to the surface. One of the reasons that we did that is because we started right off the bat to see some pretty interesting rocks. This is a rock called Link, as we named it. And what's really interesting about this is it looks almost like a piece of cement from an old sidewalk that somebody's broken open with a sledgehammer. You can see a number of pebbles in here. You can see where they're weathering out, falling down onto the surface. And what's really important is you can see that they're fairly rounded and sorted. What that tells us is that they had to have been transported by water. They're too large to have been transported by the wind. They're too sorted to be just the result of an impact or volcanic eruption. And they're too rounded to say that they just sat there in place and somehow weathered out of a rock. So what we have here, and what we've seen in different outcrops that we've looked at as we've driven across the surface, is one of these gravels that's associated with the fan of sediment that I described that washed down from the north rim of the crater. And what's important about this is the size of these pebbles tells us something about how much water there must have been to transport them. And it was probably about as deep as this table is tall. So that's not to say that there was constantly water 2 or 3 feet deep flowing down the wall of Gale Crater, but it does mean that sometimes that was occurring. And a good way to think about that is that Death Valley example that I gave before again. It's dry there the vast majority of the time, but every once in a while they get a thunderstorm, and those valleys and those channels fill up with water and flush sediment out onto the fans. And that's what was occurring on Mars. Very, very different than the cold, dry place that we see there today. So that's one of the fundamental sort of results that we've gotten to so far. And this just shows the context of that valley draining down here that we've dubbed Peace Vallis, the alluvial fan of sediment that was washed out. And right down in through here is where we've been sampling those sediments, kind of at the end of that fan of debris. Well, after sampling those sediments, and Link, which I showed you before, is right over here, we still headed off to the east, and now I'm going to tell you why we did that. I noted that there were some interesting rocks off in that direction. And what this map does is it colors different kinds of rocks that we saw from orbit. The green is one type, the blue or purple is another, and this brown is yet another. And they all come together right in this area that we call a triple junction. We dubbed that Glen Elg or Yellowknife Bay. And those 3 units that we see in this location are actually seen all over the floor of Gale Crater. And so if we could go and study those here, we could get a good sense of what's happening across the floor of the crater. And that's why we headed off towards the east once we landed, rather than towards the south and west. And this is the kind of thing that we saw. This area is called Point Lake, and down in through here is an area that we dubbed Yellowknife Bay, Point Lake. And here's another area just to the south of Point Lake called Shaler. And you can see these sort of sweeping beds of rocks through here that, because they're inclined, show that sediment was being transported along these surfaces. And what we're trying to discover here is whether or not these sediments are related to those fans of debris that I talked to you about before, Link, that were washed down the wall of the crater. Because if they are, the sorting, the regular size of the grains in here, and their fine-grained nature of at least some of these suggests that they were really far out at the end of the fan and might actually record where that water that was draining down the fan was ponding into a shallow lake for a time. And we decided to go here and put down our drill and drill into these rocks and see, in fact, what they're made of and what they represent about past conditions on Mars. And really what we came up with was that this rock is filled with a bunch of clays. Phyllosilicates basically mean clays. This is from one of our chemistry labs, our chem-in inside, where we zap it with X-rays. And every one of these circles that you see here represents the diffraction of X-rays related to certain crystals. And what we see down around the center here that we didn't see in other places is that there's a lot of clay in these rocks. And when you put together the color of the material, the clays that are there, the fact that there was probably water associated with the formation of these clays, what we get is that in the Yellowknife Bay area that I've been talking about, we in fact did have an ancient environment that was habitable. We know that these fine-grained rocks represent past washes of water coming down through the surface, perhaps ponding. We know that the mineralogy, the clays that are there, tell us that that water wasn't too acidic. It was just right in terms of sort of neutral pH. It tells us that there were things that were key to life, such as carbon, nitrogen, oxygen, phosphorus, and sulfur that were present there. And it tells us that the minerals in various stages of oxidation would have provided a source of energy for primitive biology. So this isn't to say that we found life on Mars, but what it does tell us is that in these early days of the mission, which will continue for at least another year and perhaps for years to come, we've already discovered a place on Mars where 3.5 billion years ago, the conditions certainly were habitable as we consider them here on Earth, but on Mars. So with that, I'll stop and ask, I guess, if there's time for any questions.
So I'm Griffin Esslinger from South Carolina, and I'm wondering, would it have had to been liquid water, or could it have been some other kind of liquid substance?
Good question. We know from the temperature range, and we know from the kind of minerals that are present and how they would react with different things, that it almost certainly had to have been water, and it could not have been ice. The sorting of the grains, the chemistry of the grains, tell us that it certainly had to have been water and probably liquid water. So we're fairly confident about that interpretation.
I'm Grace from Connecticut, and does Curiosity pick up most of the rocks it finds, or does it leave most of the rocks?
Good question. Well, we can drill into the rocks, as you saw, and we've also got a thing out on the end of our arm that can scoop into sediment. And we can either take the drill tailings or the scoop of sediment and dump it inside the rover, and we can keep it in there for a long time and analyze it again and again and again. But ultimately, we dump those things out on the surface, and we don't actually save any chunks of rock or scoops of material. So we can keep them for a while, but we actually get rid of them all.
Hunter from South Carolina, you said that it was most definitely water and not ice, but in your PowerPoint you also stated that the average temperature was negative 81 degrees Fahrenheit. How would the water be there? Was it a difference in the atmosphere 3 million years ago?
That's an excellent question and a good observation. Mars today is cold and dry, way, way below 0 Fahrenheit, Celsius, Kelvin, whatever scale you want to use. It is, as we used to say in northern New York, but cold. So there's not a lot of water flowing on the surface today, although there may be some. We've detected some in some high-rise images that could be where the sun shines on rocks in the peak of summer, some moisture that's draining across the surface, but nothing like what I've been talking about. So what happened? Why is it that 3.5 billion years ago, the surface was wetter? And you put your finger on it when you said that the atmosphere was probably a lot denser. We know from the chemistry of the atmosphere that there used to be more of it than there is now. And the idea is that a denser atmosphere is more efficient at trapping the sunlight, a greenhouse effect, that then allows that environmental condition to warm up to the place where liquid water becomes stable.
Hi, my name's Claudia from Fitchburg, Massachusetts, and I'm just wondering, how do you go about naming the areas and who names them?
So, and the same thing happens on the Mars exploration rovers. We pick themes. On the Mars exploration rovers, I remember as the seasons changed, for example, we had a time where baseball players or baseball kinds of things were used, or ships of discovery, for example, are used to name the major craters that we see. For the Curiosity rover, there's an area up in Canada where there are very ancient rocks that here on Earth were used and are used to try to understand what early conditions were like on the Earth. How did life get going here? And that's very much in line with the goals of Curiosity in terms of understanding whether or not Mars was habitable. So we decided to, at least for now, for this first 11 months, and probably for some months out into the future, use names from that area in Canada, Yellowknife Bay, for example, that we could then apply to different surfaces and rocks on Mars that sort of brings that idea of what we're trying to do to the mission. As a long-term planner, we're in charge of sort of producing that list of names and assigning those to different rocks as people propose them.
Let's thank Dr. Grant.
Thank you all very much.